Exactly what it does when you click it, but I have clicked it before, and it causes problems, so...
Spoken like a true reactor operator. It's time for some more Roblox. Specifically, Oak Ridge Nuclear Power Station. Not to be confused with Oak Ridge National Lab. For those of you who don't know me, I'm Tyler Folse. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry. From engineering to operations to emergency response. No claim to know everything there is nuclear, but I can certainly share some knowledge.
Hey everyone, today I'm going to be showing you how to set up the nuclear reactor in
Nuclear.
Oak Ridge Nuclear Power Stations.
Okay, so looks like they have a few doors, some security doors before entering the control room. That's realistic. Access is very tightly controlled at a nuclear plant.
So, basically, what we're going to want to do, first off, let's grab our key back here, the key cabinet, hit one of the operator keys.
There are indeed some key cabinets, though you usually don't use the keys for much within the actual control room. They're usually handed out to plant operators or certain instrumentation and control technicians to access certain specialized equipment in the field or the relay room or some other secure location. But sure, I know some control rooms do make use of keys.
Whatever it's called, and we need to start with pre-start. So, there's 2 steps to setting up this reactor.
He's actually got checklists. That's awesome. They've incorporated procedures and paperwork into this game. This might be the most realistic Roblox mod yet. Do you have to get peer checks and sign-offs? Do you have to wait hours in-game to get in touch with the right department manager?
Pre-start, and then there's startup. We'll go to that next, but first of all, we need to, do the pre-reactor startup. So, it says off here, condenser coolant pump A1. So, that's referring to over here, which is the coolant pumps. We need to set off A1 and A2. So,
okay, so right now he's in the secondary part of the plant, and so condenser coolant. So the plant I worked at, we call this the circulating water system. That is to say, the reservoir. Looking at this control panel here, it looks like they're using coolant towers, but same principle. Sole purpose is to pump water to the condenser and cool it off. It's the tertiary loop of the system that supplies the secondary or non-nuclear part of the plant, the condenser, which receives the exhaust from the main turbine that produces the electricity. Important in any power plant that uses a steam cycle. You don't just see this in nuclear plants, and it isn't just nuclear plants that has the hyperbolic cooling towers. The plant I worked at didn't actually have cooling towers, it just had a really big reservoir.
That would be these 2 right here. Click. And just like that. That's the first step.
Okay, I've seen this in a few different of these games that I've looked at, but at the plant I worked at, red meant on or energized or open in the case of a valve. But here it's it looks like it's backwards, where green means on and red means off. Closed, de-energized, that sort of thing. I do know that depends on what control room you go to. I want to say it was green means energized in the Navy, but I was never actually in the Navy, just hearing that from my coworkers, but that's fine. As long as you're consistent and as long as that's what you're trained on. No issues there. And yes, this startup checklist, there are now startups at real nuclear plants do come with checklists, but it's more of what section of your big procedure did it tell you to do. Usually there's detailed instructions on start this pump. There's a few notes and cautions about, hey, what sort of things that you need to consider when starting these sort of pumps, what sort of things you look at, such as temperature in your condenser, vacuum in your condenser, that sort of thing. But checklists are a good operator aid, and it's funny how they put that into a video game. I love it.
Startup. Now, something that's really helpful, which I will mention here, when you're clicking around with buttons, it's really good to kind of line your camera up and then click F.
Interesting component of something being harder in a video game than it actually is in real life. F to presumably focus.
Allows your mouse to let go and move about, which is pretty nice when you're moving around with buttons and trying to get precise with stuff in a limited amount of time.
Full disclosure, I've never actually played this game before. I'm mainly just going to be reviewing it and seeing how it compares to a real nuclear power plant.
So, next up, we're going to do turbine A, B bleed valve, and A bypass valve. So,
loving the amount of coverage the secondary plant gets in this game. A lot of times in a lot of nuclear simulators you see, as far as video games go, it's mainly just the turbine, and it might as well just be a black box that says, here be steam. But yes, you're going to be using the turbine bypass valve, or the steam dumps as I called them in the plant or the steam dumps as they're called in the plant that I worked at. And that's because the turbine's offline. You're just starting everything up. You actually take the reactor critical and online before you sync the turbine to the grid. But you have all the warm-up steam in the secondary part of the plant, and it's got to go somewhere. So through the turbine bypass valve, straight to the condenser, because the turbine's not in service right now.
That should be right here on the turbine A control in steam turbine generator A. You want to turn this one on right here, and then that one on. And that's these two. Now, turbine A bypass valve, 100%. Now what that means is that we need to get this here, that's at 0, we need to get that up to 100. So pretty much, it's as simple as...
Okay, that's a notation I'm used to, 100%, just 100% demand, which means the valve positioner would take it to full bypass.
Coming down here, as you can see, there's the turbine valve and then there's the bypass valve. We want the bypass valve to get up, so we click loose on full and increase flow, and it should start moving up. And once it hits 100, we're done with the spot for right now.
Not sure if in the game, if this is demand on the valve positioner or if it's actual valve position. In a real nuclear plant, you'll see both. That way you can tell if something's acting funny with your valve positioner. And what that would look like is the valve positioner demand would say 100, and then actual position would drift to 100 over the course of a few seconds. But I can see for the purpose of the video game, no need to overcomplicate it.
There we go. Bada boom. So we took that off the list, and we move on to the next bit. Deerator A bleed valve.
I like that. Good placekeeping there. Make a good reactor operator.
Is right here. Now, we will come back to that later, but for right now we're good. So take that.
One thing I will point out is this: if this was a real simulator level of a game, you would not be doing any of these operations by yourself. You would have a buddy with you as a peer checker and then another person as a supervisor. And we regularly play video games in the nuclear plant. It's a full simulator that's about as accurate as you can get, because it looks exactly like the real control room. Not 100% accurate. I mean, there's a few things that can only be done in the real world, but pretty close. But like any other video game, it's susceptible to a bit of lag.
Off, and we need to do Deerator A relief valve 50% and steam inlet valve 25. So
not sure what it means by relief valve. Usually when I think of a relief valve, it is something that spring actuates due to overpressure. So that isn't something you actually control. Now, it could be a power-operated relief valve, as in the thing that you lift before the safeties actually lift. At the plant I worked at, we referred to it as a pegging valve, so it modulates based on steam demand and the actual back pressure within the deaerator. Interesting, they're actually using a deaerator. A lot of times this would just be your feedwater heaters in the secondary part of the plant, but whoever made this game apparently understands the benefits of secondary chemistry control, that you want a proper deaerator to filter out all those non-condensable gases. Not every nuclear power plant has them.
It's pretty much just saying it wants Deerator A, it wants this one to be at relief 50 and then 25 on the left. So same as the last one, is increase and decrease, you want to increase. Just want to make sure here, relief is 50, that's correct.
And this is all about sending main steam to the deaerator. So the deaerator does preheat water that is going to be fed back into the steam generator to improve secondary cycle efficiency. But some of that steam is extracted from the turbine and provides a bit of preheating to overall increase your thermal performance.
Okay. And actually another helpful thing.
Not sure how many strings of feedwater heaters they have. They could just have the one for the purpose of the game, but hey, the fact that they include secondary components at all is remarkable for a game about nuclear reactors, where a lot of people neglect this stuff. I'm glad it's in here.
You can move about while you're holding. So you don't have to sit by the button or camp it. You can look about and do your own stuff. It's, you know, you're holding it, which is pretty good.
Just one of the reasons why you have multiple reactor operators. Because there'd be someone watching the primary system, the reactor coolant system, even while it's offline. And there would be activities taking place in both parts of the control, both the primary and the secondary part. During an outage, which is, in this case, you're going to be recovering from an outage, there's often 10 or so people in there. And during normal operations, full power operations, there's at least 2 reactor operators and at least 2 supervisors in there.
But there we go. We have done these 2. Now, automatic feed limiter. Simple as coming over here on the feed water system, separate feed water pumps, just turn that one on. Turn that one on there, and yep. Here we go.
Okay, getting your feed water demand system, and that's a integrated system that looks at steam demand, feed water demand, and level or water inventory within your deaerator, and it all maintains a flow balance. Requires a good bit more manual oversight when you're at low power, when you're starting up, but it basically operates itself when you're at full power. That's the main thing about nuclear power plants. They're designed to have all their systems in automatic when you're sitting at 100% power. Steaming and dreaming, as we call it.
Injection tanks? Alright, we're done with this side for the minute. We need to come to over here. And what I mean is that we need to start here, so...
Okay, so we're in the emergency core cooling system. It is to say this system that you have it armed after you've started up, but it doesn't actually operate unless you really need it, such as you have a loss of coolant accident, for instance.
When you get this tank up to 1500, as it says there, so basically we just turn on the nitrogen and we wait for that knob right there to get to 1500.
Okay, so pressurized system. The plant I worked at, this was called the safety injection accumulators, and they are basically pressurized tanks that inject water first during a sudden loss of pressure. They're usually kept at around 600 psi, but the reactor coolant system, at least in a pressurized water reactor, I haven't seen the reactor screen yet, so I'm not sure what type of reactor this is yet, but when reactor coolant system pressure drops below that, they automatically inject, empty their contents, and then the pumps start providing more water to keep the core cooled, covered, and properly reactive in the event of an accident. But yes, in the event of a plant startup, you're going to be arming these systems when you get to a certain point in reactor coolant system pressure.
I'll just speed it up here for you.
Pressurizing those tanks often takes days, so I'm pretty sure in a video game they're going to make that faster. Must have a highly pressurized nitrogen system.
Okay. And
this sort of stuff, very much within the acceptable breaks from reality for the purpose of making an engaging video game, and not the hurry up and wait for 3 days to watch paint dry from the perspective of the simulator. Even in training exercises, we speed up stuff like this, because really the point of training is to get the crew briefed. You're not really adding any value running a multi-million-dollar simulator for 3 days with your operators not doing much.
here we go. As you can see, click E to zoom in actually. Sorry, I forgot to mention that. It's really helpful when you're looking at dials and stuff. That's pretty much right. You can go slightly off and a little under, but...
Not sure what the units are. If it's PSI, I haven't seen an indication if we're using metric units or not. The plant I worked at in the US did not use metric, for the most part. Used metric on a few things.
Never go into this sort of area, like... Try to stay away from here and here, just stay...
Stay out of the red bands. Yep, that's some classic Operations 101.
Right down here, in this area, when they say 1500. What I'm basically saying is you don't have to be too precise. Now, Take that off and we need to move on to hot well level 35.
Okay, wow, 1500 psi for so it is PSI for ECCS injection. That's a lot. But hey, every plant's designed a little different. Basically, that means they're going to inject if reactor coolant system pressure gets below 1500 psi, and the rate at which they'll inject will depend on how much lower than 1500 psi it is, which would depend on the size of your reactor coolant leak or whatever accident you're facing here.
For hot well level. So that's this one right here. It says we need to put in the code 35. So you put in 35 now. Don't click this button yet. What you want to do, you want to do the second thing here and turn this on. So there's some way to go. I'm pretty sure. I think so. And
all right.
Yeah. Okay. Now
another automatic
64 offload system. That's basically telling you to come over to the generators over here, and you want to hold for 5 seconds to prime offload. So
okay, this is weird. You're putting the electrical plant near the primary rather than by the secondary. You should put your generators next to the turbine, because that's where it is physically. It's called a turbine generator system. That's kind of an unusual layout to me. Basically, you're gonna have to run back and forth, and considering how a lot of these video games are operated when you just have one person, that's a lot of running around to do. Maybe they did it so there'd be a lot of running and jumping like you typically see in Roblox.
You just... Whoa. Weird. Okay. You just hold that for 5 seconds and the light should turn. Like so. Do not click that light. Never click that light when you're in operation. I'm not sure exactly what it does when you click it, but I have clicked it before and it causes problems, so...
Written like any note of precaution in any procedure. I'm not sure what this does, but I just know it's bad. Spoken like a true reactor operator. I love it.
Just... You never want to click that when you're working in your... when your reactor's working. But anyways, now you want to...
Okay, things that you don't want to touch while your reactor's online. I'm not sure what that would actually be. It's not like there's a generator trip button. You usually, if you're going to manually trip the generator, you do that by manually tripping the turbine.
Now you've done that, automatically you want to offload. Click that one there. Click that off. And now breaker 18NG1. That's this thing right here.
Okay. Getting your electrical lineup situated.
So you insert that, and you turn that on. Ba-da-boom.
Okay, so operating breakers with a key. That's different. I've never seen that one before. I've heard of manually resetting a breaker after its protective relay flag actuated, such as if it was an 86 lockout device. And the reason for that is the breaker sensed something overheating to such a degree that it really did not want to reclose by accident for fear of starting a fire. So that's why those things exist. But as far as keys to close breakers, I haven't seen that.
That off, and now breaker 64BN. That's this one right here to the right of it. Just turn that on.
Okay, so you're getting your electrical lineup. Good. Okay, so your auxiliary transformers and your auxiliary transformers supply house loads as opposed to your main transformer, which supplies the grid. Both of those are fed from the reactor, and by that I mean the main generator's output breaker. While one unit is offline, you are typically supplied by the grid, or if you're a site that has more than one reactor, by the other unit, the other reactor.
Now, head back over to the condenser pumps, where we were at the start of this, right on the very end.
You see, it's not very ergonomic. You gotta walk all the way over to continue this sort of thing. Usually I'm used to the electrical plant being right next to the secondary part of the plant.
And you want to turn A1 and A2 speed up to speed 2. Now, that is speed 2. So with these things here...
Interesting.
Basically, there's free lights above most of the main switches on a switch above that. And like I said, there's free lights. Now, these are the 3 different speeds. This isn't 0, mid, and then on. This is speed 1, speed 2, and speed 3.
Yeah, in a real nuclear plant, you're not going to see variable speed pumps that are that large. These pumps are ginormous. The actual impeller goes multiple feet into the ground or the reservoir, or whether it be a circulating water pump, feed water pumps to a lesser extent, and certainly reactor coolant pumps or reactor recirculation pumps, depending on if it's a boiling water reactor instead of a pressurized water reactor. These are ginormous, many thousands of horsepower pumps. Variable speed is rare and tightly controlled, and it's going to be on much smaller components. I've never heard of any variable speed pump that's that large.
Just want you to keep that in mind. Like I said, speed 1, speed 2, speed 3, that goes for every switch like this. Okay, so middle is speed 2, and we have done that. Now, we want to move over to the main circulation pumps, which are these. This is the water that flows into our reactor. We want to put A2 and A1 to speed 2. So
water that flows into it. Okay, so we're now going to be in primary systems. So circulation system. So they must be referring to the reactor coolant system. So, all right, so judging by the name by itself, that implies it's a boiling water reactor. That's not a word that's used. So that begs the question, why have your emergency core cooling system accumulators at 1500 psi, considering that's higher than most reactor coolant pressures at boiling water reactors? Boiling water reactors, you're only at about 1,000 generally. You're in the 2200, 2300 range for a pressurized water reactor. Now, maybe in this design, they keep the injection valve closed and you're required for it to open, but that's a bad design. Because it's not passive. It's not a passive safety system. You're dependent on a valve to open, which is why you normally keep them at a lower reactor coolant pressure. Because otherwise, as is, even at normal operating pressure, your safety injection accumulator is going to inject because 1500 is bigger than 1000 psi. So it either wouldn't work, or you needlessly made a passive system an active system, which isn't good.
that is this one. And this one.
So variable speed reactor recirculation pumps. Also, are there sets of 3? That's a lot of pumps. A large pressurized water reactor or boiling water reactor, depending on your design, you're still on the order of 2 to 4. And this is, I don't know if these are in series or what.
And yeah, now last things, come over this on the...
Or to control flow, you're going to want to adjust valve position, not have variable speed pumps. I mean, you could theoretically design it that way, but you might find yourself running into pressure gradient type problems from having pumps this size at different speeds.
Main panel here. Over here, we want to turn inlet and outlet on. So on both of these. So inlet and then outlet.
Isolation
like
valves. Okay.
We're done. We're done with reactor startup now.
Okay, you're done at least as far as, I guess, flow path startup. Starting up, turning pumps on, opening valves, and energizing breakers. I mean, that's really what a lot of it is. Albeit this was pretty condensed, but not bad for a video game.
We can put this away. There's no need for it after this. We need to move on from over here. We need to move on to reactor startup. Now this is the real stuff. This is the good stuff.
And where a lot of these game simulators would usually start, they just assume, okay, your secondary plant's set up already, and it responds to steam demand magically.
This is what we need to do. This is how we turn on the reactor. And we get operations going and power flowing to our grid.
So this Scrabble board right here is showing where all the fuel assemblies are located. Sometimes it tells you the enrichment value, sometimes it doesn't. A lot of times you just reference a nuclear design report manual that essentially tells you things like that. It tells you what each control rod is worth. And by what it's worth, I mean how pulling one rod would affect reactor power both globally and regionally. Hence having the grid up so you can look at power peaking.
We need to initialize reactor mode 1, which means this button over here on the main panel. We want to click mode 1. Easy, yeah, an alarm should, oh, there we go. An alarm should start. Mode conflict, this tends to happen when you switch between, just acknowledge it. And move.
Oh nice, they actually have silence, acknowledge, and reset things, so you don't have to listen to the alarms blare like you do in certain simulators. That is a good idea. Granted, I'm used to silence being on the left, but that's because I'm used to telling operator to say silence, then acknowledge, so the alarm will start flashing. And you'll get a ding sound noise, almost a cash register noise when the alarm condition has cleared, and then reset clears that button. I'm glad they incorporated this into the game.
Now, what you want to do, tick that, and I'll play.
Mode 1 doesn't necessarily mean anything to me. When I'm used to hearing reactor modes of operation, it's Mode 1's power operation, Mode 2 is a reactor startup, Mode 3 is a hot standby, which is probably where we should be at this point. So all the secondary plant warm-up and startup, I think a couple of days would have just passed at this point. Maybe longer, depending on how long it takes and what your chemistry technicians tell you about their samples they get in both the primary and secondary loops, saying that you're good to go. Anyway, I don't know if they would incorporate chemical sampling into a game like this. Seems like a different audience.
Cool. So, basically just turn these two off to the right of here, and come down here and turn these two on right there. Circulation pump 1 and 2, or turn it off, sorry. There we go. And now you can...
Okay. Maybe those were the low power versions, switching low power components off and getting ready for operation. Or not low power, standby related components.
So, now we need to shut down A3 control rods, which is this one right here. So we just click that, and as you can see...
So wait a minute, so those are the shutdown control rods. I think he means withdrawing the shutdown banks. So any nuclear reactor is going to be designed such that you have both control rods or control banks and shutdown banks. These shutdown rods are basically additional rods that you're going to have to give you all kinds of shutdown margin. And by shutdown margin, I mean more than what is necessary to keep your reactor shut down. So withdrawing those, you're not expected to take the reactor critical where you're making fissions in steady state. That being said, any reactor operator worth their salt is going to be trained when doing any form of positive reactivity addition, such as withdrawing your shutdown banks, to expect criticality at any time. But in reality, you're going to have a reactor, a peer checker, a supervisor right next to them, a team of engineers monitoring on their reactivity computer to see the effect of every single rod withdrawal. That, yeah, it's going to become glaringly obvious when you take the reactor critical or not.
If you look at the blue rods, they are going down. Our shutdown rods are coming out of the reactor. So I'm just going to quickly explain as these come down.
Alright,
There's three sets of rods in our reactor. There's the blue ones, which are the shutdown rods. Those are what are coming out now and what will allow us to work on our reactor. There's the red rods, which we will talk about in a minute. Those are or we will use in a minute actually. Those are the auto rods, which is basically the computer deciding which rods are to go in and go out and moderate our reactor. And
automatic
the ones with no color is our rods. That's what we decide.
That is immensely weird. So all rods during reactor startup are either in a boiling water reactor should be operated manually when you're controlling it. Now rods in automatic, what that is useful for is if you're parked, you're not raising reactor power or lowering reactor power, to enable the rods to respond automatically to a plant transient and insert to lower power due to, say, a turbine load rejection, for instance. So temperature, flow, your void coefficient, all of those key parameters in a boiling water reactor are kept where they need to be. Not some of them in auto and some of them that are auto exclusive and some of them are manual exclusive. I mean, you could theoretically design something like that, but that's bizarre. Shutdown rods are all going to be manual, and usually you have like several different shutdown banks, but I can understand just one for the purpose of a video game. But yeah, that's bizarre. And usually you're going to see two different numbers. You're going to see actual rod position, and you're going to see demand of what your control system is taking the rods to. So that's also a bit different.
That's where we decide which ones come out. That's our rods. So, yeah. Let me see. Okay, let me just speed this up one sec. Once this is over, you should hear a little bell.
For when that alarm clears, the mode conflict.
Okay. Yeah. That's the bell. Sometimes it happens a little after, sometimes it happens a little before. Just depends. But yeah, the bell's off and we're cool. So now what we want to do, we want to just quickly, we can tick that off and we can raise reactor thermal. In fact, okay, just gonna silence that or reset that so it stops blinking the mode conflict. So raise reactor thermal. I'm just gonna real quick, this is optional, you do not have to do this. I'm gonna turn off auto scram. From what I know,
that is a horrifically bad idea, because you're gonna want automatic you're gonna want the reactor to automatically protect itself in case when you're doing a reactor startup something unexpected occurs and you have an unexpected power spike. That is a safety function. This is some Chernobyl level thinking right here.
basically, this loves to go off, but from what I know, it makes the reactor really easy to shut down from some issues. Like, say now we have an issue.
That's a great thing. That's what a good reactor protection system is designed to do.
That is still fixable.
That is still fixable. Okay. Now, so that gives to the question, is your reactor protection system too sensitive? And that could be a real thing. So, I mean, I know it's a video game, and clearly this guy's doing the sensible gamer thing to do in order to essentially beat the level and move on. I get that. But in reality, if you had an oversensitive reactor protection system, that's going to involve your instrumentation, engineers, and technicians to troubleshoot and correct the issues associated with it, and the reactor will remain offline until that sort of thing is fixed. You're not going to start up the reactor anyway with systems defeated just to get around this sort of thing.
The auto scram catches it, then it just AZ5s. Yeah, it just scrams the whole reactor.
The fact that there's a key switch that does that is baffling to me. You can defeat what does exist is you can defeat certain low power reactor trips. That is to say, there's a reactor trip at 25% reactive power, for instance. But when you get above 10%, hey, you have the option to say, okay, do I wish to continue? And then you defeat that so you can get above 25% so you can take the reactor to 100% power. There will be an indefatigable reactor trip at, say, 103% power, for instance, that will trip you on overpower. There's about 10 different ones that do that sort of thing, not strictly 103% power on one indication. But anyway, the point being, there are certain reactor trips at low power to prevent let's say a rod pool goes disastrously, the reactor core had way much more reactivity in it than anyone initially thought, the engineers screwed up in their calculation, the reactor's going to protect itself by turning itself off.
Pushes all the rods in, and that can lead to problems, so there's no need for it, but it's up to you, really. But now, we need to get to pulling rods, so...
Look, nothing against this guy. I know he's just playing a video game. That's fine. That's fine. But I'm just saying, there's a reason why this function doesn't exist in a real nuclear power plant.
Reactor thermal, basically what we want to do before...
Except for Chernobyl.
We start setting rods. We need to turn on the auto rods, which are the red ones, as I spoke about. So, let's turn this bad boy on, right? And now we have auto rods, and basically... to get these to work, we need to put in the amount, which is 1500 at the minute, so we put in 1500. We set that, and if you take a look...
So reactor startup, to go up to, say, 1500 megawatts, there's going to be various stages, various pumps you turn on, various holding periods that you would get to for chemistry control, for engineers to come in and do a flux map, all kinds of things that you would hold for long before you get to 1500 megawatts. Also, why are we going to 1500 megawatts before syncing the main generator to the grid? You'll do that at a fraction of that load, like 200 megawatts at most. Otherwise, you're just wasting fuel here if you go up to 1500 before you sync the generator to the grid.
They're starting to pull out, is trying to turn on the reactor so it gets to that mode, but we need to moderate it with our own and bring it out. So, basically, this is a pattern that I learned from another video. I'll put them in the description because they're pretty good, cool. We pull these out, and then we pull those out, and then, or we click those, and then, whoa, sorry, excuse me. Excuse what I do with it.
Is he inserting control rods while withdrawing other control rods simultaneously?
Oh, okay. Missed that one. Alright, so here what I'm going to explain, you can only pull out 12 at a time, so as you can see, we kept it symmetrical, and we have 12. 1, 2, 3, 4, 8, yeah, 12. So
a lot of these are built in the rod control systems. This is called bank overlap, so you keep your power distribution symmetrical, and you don't really have the option unless you're at extremely low power and doing some sort of low power physics testing that you would even have the option to select individual banks like that.
we could just remove those, and eventually power will start to come up as they almost come out. So I'm just going to speed this up here.
Okay, and they have this thing called reactor period, which is a bit weird, and I have only seen in boiling water reactors. This is a weird unit. So it's given in seconds, and it is the amount of time it takes for reactor power to increase by a factor of E. And that E is the 2.7 and change number that mathematicians love. That is counterintuitive. What I'm used to seeing is startup rate, which is in units of decades per minute. A decade's a factor of 10. And a large commercial nuclear power plant, you're not to exceed 1 decade per minute. So going up by a factor of 10 per minute. Compare that to a nuclear submarine where the limit is 5 decades per minute, which is a factor of 100,000 in a minute. And during a fast recovery startup, that is 9 decades per minute, which is a factor of 1 billion in a minute. Clearly, a submarine is analogous to a high-performance sports car, and a commercial reactor is analogous to a freight train. I much prefer startup rate because that's more intuitive to me, but I guess for those of you who are mathematicians that swear by E, sure, reactor period is perfectly fine. Okay,
just like that.
I see neutron flux is going up. That's often proportional to reactor power, and really another different way of measuring reactor power.
We're getting power in our reactor. Reactivity is happening, or fission, or whatever. It's happening, and
really, you're fissioning long before your power meter came on scale. You're going to be measuring it in something like counts per minute long before you get to your nuclear instrumentation registering in the power range where you express it as a percent or you express it in megawatts thermal. Now, what he might be referring to is the point of adding heat is about 1% power, and that's where you're actually going to see heat from fission as opposed to other sources of heat in the reactor, such as your recirculation pumps. I mean, they're large pumps, they're going to generate some heat.
Yeah. But see, we're only at 250 at the moment. Ooh, money. And
what is this? Oh, you get little paychecks that show up? That is hilarious. Well, of course you're making $0. You haven't synced it to the grid yet.
we need to get to 1500, so let's pull more rods out.
Oh, you getting paid for hour, $14 an hour. Man, this must be set way back in the day. Reactor operators can make some good money, especially because you're running the entire control room by yourself. I don't know, I'd ask for a raise or leave at this point. Even back in 1983, so that'd be worth about $45 now, which is decent, but for someone who goes through the intense licensing process, you get a reactor operator license, that's still going to be low.
Remember the right pattern here, because I have failed multiple times by doing the wrong pattern, so let me think. I think we just want to simply...
By failed, you mean the reactor tripped, or you mean you damaged your core?
Do one of these, and then do that.
Yeah, you would realistically have procedures that tell you which one of these things to press if you did operate the reactor like this, where you have your manual control rods fighting your automatic control rods, which is a really good way to get in trouble with the Nuclear Regulatory Commission if you designed it this way.
And then these two, and we'll give that a go. If a problem happens later, then So strike they did. Yeah, as you can see, like that, and just remove those, and don't remove them all the way, just remove them till we get to 1500. You can go a little over, but hey, it doesn't really matter. The automatic roads will moderate it itself. As you can see, they're all the way out of the minute, so we want to get them more.
If you went a little over 1500 megawatts, then your automatic rod withdrawal system is crap. I'm saying it. These things need to be designed precisely.
Them in. That would be great. So I'm just going to speed this up here.
So 1500 megawatts, if I'm reading that correctly, is less than 1/3. So this reactor nameplate capacity is north of 4,500 megawatts. That's bigger than the reactor that I've worked at. That one was about 3,850. Wow, this is a big one.
Okay. We put it slightly over because I just want more of the reds to come in.
Slightly over. By that we mean 100 megawatts over. You need to go ahead and get that turbine online, drive enough reactor power this high.
So that should moderate it.
Probably multiple turbines for a reactor of this size.
So as you can see, it's going down and those are going in. So now, as that's doing that, we'll wait for it to come down all the way, and then just might as well take that, and then we can get onto that. If there's a alarm in a sec for you, then that's totally normal. Or at least an alarm.
Don't forget to curse the Deerator on your way out. Someone really doesn't like the secondary plant, or you have a cursed one.
That's normal, we'll fix that in a minute. That's the next step. Okay. Okay. And just like that, we are at 1500. Okay, now we want.
There you go. You only overshot a little bit and then came back in. I would, if I was your operations manager, I would definitely be writing up your crew for that. That's not great.
Initialize mode 2, which is operating mode.
Ooh, okay, this is kind of backwards. So I'm used to mode 1 being operating mode, and you enter it above 5% reactor power. That is to say, all of your normal operating systems are going to be online at that point. It's just going to be a question of how many pumps you have turned on and what their specific flow paths are. But as far as the physics concerned and the accident analysis is concerned, you're definitely in mode 1 way before you get to 30% power. But here, I guess we're going backwards. Mode 2 being normal. To me, that sounds weird, but okay. However you want to define your systems.
Alright. There's the alarm I was talking about. We want to turn on feedwater and condensate 1. So, condensate pump 1.
You mean to tell me you didn't have any of your feedwater and condensate pumps running and you were this high in power? Where was your steam going? Were you just exhausting it to atmosphere? Wow, that's 1,500 megawatts of steam. That is a massive plume, all going to atmosphere. You can make a sizable plume for 3 or 4 megawatts of steam, enough to fill up your entire turbine building. That's the implication without having your secondary loop fully forward feeding.
And we want to enable it to speed 2, and we want to do the exact same thing with feed 1, which is over here below the buffer. Now it should begin to fix itself. If you're a ding.
That's good reactor operator behavior. It should begin to fix itself. Hey, I love the design margin they put into this sort of thing.
Another ding. Just acknowledge. There we go. We are cool. Alright, so we have a sufficient feed.
There you go. You made the annoying noisemakers stop. It's an important part of being a reactor operator. I know I'm saying these things, but really and really, this is a good mod to get people who are curious about nuclear power and what a control room is like, what power generation is like. It's pretty good.
Reactor. Thing with condensate and feedwater, you can't have one without the other. So if you see condensate speed 2, you know that or if you see condensate 1 at speed 2, then you know that feed water 1 is going to be at speed 2, and that goes.
Okay, good. So you're basically matching your condensate to feed water flows. So usually the difference between condensate and feed water is how many feed water heaters you went through. The plant I worked at, it was the Deerator or the number 2. There were 6 different phases of feed water heater, and you do in reverse order from 6 to 1. The ones are the big ones, the high pressure ones that really get your thermal efficiency going. But once you're through the Deerator, you're considered feed water. And there's even a couple of stages of pumps, feed water pumps. You have your main feed water pumps, and then you have your feed water booster pumps just before that to give you enough back pressure to get you going. Okay, I mean, this is a real important concept of matching your flows in your secondary plant.
For every feed water and condensate based tasks. So now that we've done this, one sec. We need to continue to raise power, so 2100? Okay.
Dude, 2100 megawatts, and you haven't even started running up your main turbine. Man, whoever owns this plant is not going to be happy with you with how much nuclear fuel you're wasting. Because keep in mind, this sort of process takes on the order of several days, especially if you're just now forward feeding with your secondary plant. That's crazy. And when I say forward feeding, I mean going to all the way up to your steam generator, or I guess the I should say your reactor system, because in a boiling water reactor, you boil within the reactor pressure vessel. Anyway, the point being, you need to have your secondary systems armed.
So we just put that into there. We set that.
Put it in and say go.
Remove these. Which ones am I removing? I'm removing those ones right there.
There are definitely thermal limits, by the way, and they get tighter when you get above 50% power as far as your ramp rates are concerned.
We can remove this all the way. It depends how quickly this...
Now, 2100 is still less than 50% power, it looks like in this reactor, but... Anyway.
Okay, yeah, that's pretty quick. We should be fine.
Man, having a... That's going to be crazy, just the amount of force. It's the nuclear equivalent. I'm just trying to think of when you sink your turbine at this power. It's the nuclear equivalent of jumping from a moving train onto another moving train. There's going to be some precise synchroscope usage that is going to be required to even attempt something like this. Because if you're off by a fraction of a hertz, you're going to trip everything.
Are those all the way out, actually? They are, okay. And it should be able to do it itself. I don't know though. We could bring this up to 50. I prefer it. So
you don't say.
Put another pattern here.
Having an automatic rod control system and then pressing a bunch of buttons to essentially fight something or do something in tandem with it, to me, that's just baffling.
Start with those.
Should be one or the other.
Core heat and balance. I'm pretty sure, from what I've heard, it's a nothing burger. Don't worry about core heat and balance.
Core heat balance, that's actually one of the most important things. Within your reactor, your core thermal limits are quite clearly defined within your technical specifications, and getting even close to your limits is a good way to get in trouble with your regulator. We're going to go ahead and call it a part here. Stay tuned for part 2.